So this is linear algebra lecture 3. And in the last lecture, we looked at systems of linear equations. So this is something that looks like, 2x1 plus 3x2 minus 5x3 equals 17, minus 5x1 plus x2 plus 100x3 equals minus 11. This is a system of two equations in three variables. And when we're writing systems, the convention is, and the convention that I use, is that m is the number of equations and n is the number of variables. And the set of solutions, or the solution space, in this case, for example, it's all vectors x1, x2, x3 in R3 that solve the equations. Let me just say that it solve the equations. So you plug these numbers into each equation and it's a solution. And the set of solutions is, let me call this L. L is an affine, in this case, an affine subspace of R3. An affine subspace means L is some vector V plus W, so it's a translate of a vector subspace, W by a vector V. So that's what it looks like. Again, this is basically what you learned in high school. If instead of x1, x2, let me use x and y. If you had an equation like, I don't know, 2x plus 3y equals 17, what are the solutions? Well, y would be, 3y would be 17 minus 2x. So y would be 17 over 3 minus 2/3 x. So the set of all solutions L would be all vectors x, y, where y is 17 over 3 minus 2/3 x for all possible values of x, which I could write as the vector 0, 17 over 3, plus x times the vector 1 minus 2/3 for all x in R. And this is an affine subspace, because this, W, is a subspace. What does this subspace look like? This is the subspace. Let me just draw a picture here. If you look at x 1 minus 2/3, or x minus 2/3 x, that's xy, where y is equal to minus 2/3 x. That's just a line through the origin with slope minus 2/3. That's my W. And the vector 0, 17/3, let's say that's over here. And when you translate this line vertically by 17/3, you get this. So if you take this very simple equation, 2x plus 3y equals 17, if you so this is a line, and that's the line in the plane. That's just what you learned to do in high school algebra. If 17 were replaced by 0, you would get a line through the origin. That's a one-dimensional subspace in the plane. And then you shift it up, you move it up by this fixed amount, 17/3, and this red line is the affine subspace That's the solution of that one simple equation. And exactly the same thing translates to systems of equations, except that once you're in dimensions 3, certainly greater than 3, you can't draw a picture. Okay. So yesterday we talked about systems of linear equations, and we learned a method Gaussian elimination, which is a very effective, computationally effective way to solve systems of linear equations. Because if you have a system of equations, there's certain elementary operations you can perform on the equations that give you a new system that is equivalent to the original one, in the sense that they have exactly the same solutions. And it's important always to remember what are those 3 operations. So operations on a system of equations that produce equivalent systems of equations, which means these 2 systems of equations have exactly the same solutions. And the first operation is very simple. You can interchange 2 equations. Just replace the first with the second, for example, and the second with the first. You can multiply. So you have multiplication. That means if you have one equation and you multiply it by a non-zero number, you get a new equation, but it has exactly the same solutions as the original one. And what I'll call replacement, you can add a multiple of one equation to another equation. So these operations on a system of equations give you new systems that are equivalent. And Gaussian elimination is a strategy to choose the sequence of operations in a way that simplifies your system to one where it becomes very easy to find all solutions. And that's discussed in great detail with many examples in the text. And the last thing we did yesterday was prove a big theorem that says, given m linear equations, in n variables, and these linear equations are homogeneous, that is, the right-hand sides are equal to 0. You have your linear equation equal to 0 for every equation. So there's always the trivial solution where you let all the x's equal 0. I mean, if you had 3x1 plus 7x2 plus 9x3 minus 11x4 equals 0, one solution is x1 equals x2 equals x3 equals x4 equals 0. Because if you make all the variables equal to 0, you get 0 equals 0, which is fine. So this is the 0 solution, also called the trivial solution, because it is pretty trivial. But if the number of variables n is greater than the number of equations m, that's the condition, then there always exists a non-zero solution. So this is really a very important theorem. You have a system of linear equations with more variables than equations, then there's always a non-zero solution. So that's what we did yesterday. Today, we do something new and extremely important. And that is to discuss vector spaces in general. So recall Rn, which is the set of all n tuples written as column vectors of real numbers, is a vector space. It's not the only vector space. This is really an example of a vector space. And there's a general definition of a vector space, which I'm now about to give. You might call it an abstract vector space if you like. There are a lot of vector spaces, and they're not particularly abstract, but this is the definition. So this is critical. A vector space V over the field R is a set V. The elements in the set are called vectors. In which it is possible, that is, we have some definition of to add two vectors to get another vector, and to multiply vectors by scalars, that is, numbers, satisfying these properties. So there are properties that vector addition has to satisfy, and there are properties that scalar multiplication has to satisfy. And if you check, if you're just looking at the set of all n tuples, these properties are indeed satisfied. So what are some properties of vector addition? So for all vectors u, v, and w in the set V, we have associativity. U plus V. So addition is a binary operation. You can add what is defined as an operation that takes two vectors and produces a third. So if you have u, v, and w, you can add u plus v, that's a vector, and then you can add w to that. Alternatively, you could have the vector u and add to that the vector v plus w. So if this is always true, then we say that vector addition is associative, and that's a requirement in a vector space. Second is there's a vector, which I'll write as 0 in V, such that 0 plus V and V plus 0 is V for every vector in the vector space. So we call this the 0 vector. It's an additive identity. You add it to any vector on the left or the right, and you get back the same vector. And the third property is that for all V in the vector space, there is a vector W in the vector space such that U plus V and V plus U is the 0 vector. We call this an additive inverse. And both the 0 vector and the additive inverse of a vector are unique. And the third and final property that vector addition has to satisfy is that for all vectors v and w in the vector space, v plus w equals w plus v. The order doesn't matter. So this is called commutativity. Vector addition is commutative. So you have a set V in which there is some binary operation called vector addition that satisfies these four properties. There's also an operation of scalar multiplication, that is, given a vector V and a scalar C, a number C, there is a vector C times V in the vector space. And this scalar multiplication satisfies the following properties. First, if you take the number 1 times the vector, that gives you the vector. 1 is just the number 1. Multiply a vector by 1, it doesn't change. 2, there's a kind of associativity for scalar multiplication. So for all scalars, A and B, real numbers, and for all vectors V in the vector space, if I take A, B, and multiply them, because they're just two numbers, and multiply that by V, that's the same as taking A and taking the vector V, multiplying by B, and then multiplying that vector by A. That's a kind of associativity for scalar multiplication. And there's a distributivity, a distributive law. So for all scalars A, B, and for all vectors V and W, if you take A plus B times the vector V, that's AV plus BV. And if you take A times the vector V plus W, that's AV plus AW. So these are the two distributive laws for scalar multiplication. And what are some examples? Well, of a vector space. First, we have V equal to Rn. And vector addition is defined coordinate-wise like that. And scalar multiplication is defined by C times the vector. Just multiply each coordinate by your C. So for example, if V is the vector 1, 2, 3, and W is the vector 4, 5, 6, V plus W, 1, 2, 3 plus 4, 5, 6. When you add coordinates, you get 1 plus 4, 2 plus 5, 3 plus 6. And if you multiply the vector V by a scalar, let's say, I don't know, 7, 7 times 1, 2, 3, you multiply each coordinate by 7, you get 7, 14, 21. So, and you can check that all the required properties for vector addition and scalar multiplication are satisfied. So these vector spaces Rn are vector spaces. I mean, this is the most important example, the primary example, but there are many, many more. What are some more examples that you're already familiar with? So suppose we take, I'll write it as R square brackets T. which is all polynomials with coefficients in R, the real numbers, like f of t equals 7t cubed minus 2t squared plus 11. And g of t equals minus 4t cubed plus 7t squared plus t minus 19. These are polynomials, and you can add them. So these are like the vectors in this vector space. If you add them, you get 3t cubed plus 5t squared plus t minus 8, right? So here's two polynomials and you add them. Or if I take the polynomial f and I multiply it by 2, just multiply every coefficient by 2. So this is an example of what would be vector addition if the polynomials are the vectors, and this is scalar multiplication. So this is a vector space. Or here's something from calculus. Suppose I write C01 be the set of all continuous functions f on the interval from 0, 1. So 0, 1. Just all functions, y equals f of x. And in calculus, you learn that the sum of continuous functions is continuous. And the product of continuous functions is continuous. So in particular, if you multiply a continuous function by a scalar, which is a constant function, which is continuous, you get another continuous function. In this set of continuous functions, how do you define addition? If you have functions f and g in C01, you define the sum of the two functions, f plus g of x, is f of x plus g of x. And if you take a function f and you multiply it by a scalar, c, cf of x is c times f of x. So this is your vector addition. And this is the scalar multiplication in this vector space of continuous real valued functions on the unit interval from 0 to 1. Any questions about this? So we're going to study lots of vector spaces. Again, the most important is always Rn, but there are many more. If V is a vector space, a subset W of V is a subspace if the 0 vector is in W and W is closed under vector addition and scalar multiplication. So if V and W are vectors in W, let me say W1 and W2 are vectors in W, then W1 plus W2 is in W. And if C is a scalar and W is a vector in W, then C times W is in the subspace W. So a subspace of a vector space is just a subset that's closed under vector addition and scalar multiplication, and it's not empty because it has to contain 0. Okay. some very simple properties of a vector space stated in this lemma. So V is a vector space, and little v is a vector in V. So the number 0 times any vector is the 0 vector. So this is the scalar 0, and this is the vector 0. And in addition, C times the 0 vector is the 0 vector. So C is a scalar. And this, I'm just writing this very short. This is the 0 vector. I'm writing it like this to distinguish it from the number 0 or the scalar 0. Okay. So if you multiply any vector by 0, you get the 0 vector. If you multiply the 0 vector by any scalar, it doesn't change, it's still the 0 vector. And there's a very simple sort of sneaky proof of this. It goes as follows. First of all, 0, the number 0 is 0 plus 0. So that means 0 times the vector v is 0 plus 0 times the vector v. And by distributivity, this is 0 times v plus 0 times v. So here's some vector that's equal to itself added to itself. But every vector has an additive inverse. So if I take 0 times v and I add its negative, minus 0 times v, that's the same as 0 times v plus 0 times v, and I've added minus 0 times v. Of course, a vector plus its inverse is always the 0 vector. By associativity, I can write this as 0 times v plus 0 times v plus minus 0 times v, which is 0 times v, and this is the 0 vector. And the 0 vector to anything doesn't change it. This is 0 times v. So I have that 0 times the vector, any vector v is the 0 vector. That's the proof of this first statement. And the proof of the second is similar. It's in the notes. I'm not going to do it now. Okay. So any questions about this? This is just, really, this is just the definition of a vector space. So we have one concrete vector space you know and love, n tuples of real numbers. But we have other vector spaces, many others. So now we come to very important definitions. So we have a finite sequence of vectors. Not necessarily distinct, v1, v2, up to v sub k. We say this finite sequence of vectors is linearly dependent if there exist scalars x1 up to x sub k, not all 0, such that x1 v1 plus x2 v2 up to xk vk is the 0 vector. Certainly, if we let all the x's be 0, if every x was 0, 0 times any vector is the 0 vector. Adding the 0 vector to itself a lot of times gives the 0 vector. That's the kind of trivial linear combination of these vectors. But if you can find scalars not all 0, such that such a linear combination is the 0 vector, then we say the vectors are linearly dependent. For example, if I take v1 to be the vector 6 minus 14 in R2, and v2 to be the vector minus 1535, these are vectors in R2. I can do a little calculation. If I take 5v1 plus 2v2, 5v1, that's 5 times the vector 6 minus 14, plus 2v2, that's 2 times the vector minus 1535. This vector, if I do scalar multiplication, is 30 minus 70. This vector, when I do the scalar multiplication, is minus 30 plus 70. And when I add, I get 0, 0. So here I have a non-trivial linear combination of v1 and v2. I'm multiplying v1 by 5 and v2 by 2, and I get the 0 vector. So these two vectors are linearly dependent. Okay, that's an example. And if we have a definition of linear dependence, there is an implied and now about to be explicit definition of linear independence. So we say that a sequence of vectors v1 up to vk in a vector space V are linearly independent. Right? That really is the critical definition. If they are not linearly dependent, or what is the same thing, if the only scalars x1, x2 up to x sub k, such that the linear combination x1 v1 plus x2 v2 plus xk vk equals 0 are, the only time this happens is when all of the scalars are equal to 0. So vectors are linearly independent if they're not linearly dependent, or equivalently, whenever some linear combination of the vectors v1, v2 up to vk is 0, then all of the coefficients have to be 0. So for example, in R2, if I take the vector E1 to be 1, 0, and E2 to be 0, 1, suppose for some scalars, x1, E1 plus x2 e2 is the 0 vector, which is 0, 0. What does that mean? x1 e1 plus x2 e2 is x1 times the vector 1, 0 plus x2 times the vector 0, 1. That's x1, 0 plus 0, x2. That's x1, x2. And if that is equal to 0, 0, that only can happen if x1 and x2 are both 0. So these vectors are linearly independent. The only linear combination of those vectors that's equal to 0 is the 0 vector. Let me just remind you, what is a linear combination of vectors? V1 up to Vk. It's a vector which you can write as some scalar times V1, there's a scalar times V2, and so forth, and then you add up to plus xk Vk, or x1, x2, up to xk scalars. So any expression like this is what is called a linear combination of your vectors. And you have the vectors v1 up to vk are linearly independent if the only linear combination of those vectors that gives you the 0 vector is the trivial linear combination where every scalar is taken to be 0. Okay. So this is really a fundamental definition. And you really need to spend a lot of time trying to understand this concept because all of linear algebra is based on it. And one important property of linearly independent vectors is the following theorem. That V1, V2 up to V sub k be a sequence of linearly independent vectors. So the V1 up to V2 be a sequence of linearly independent vectors that x1, x2 up to x sub k and y1, y2 up to y sub k be scalars, numbers. Then x1 v1 plus x2 v2 plus xk vk equals y1 v1 plus y2 v2 up to yk vk if and only if these numbers are exactly the same. X1 equals y1, x2 equals y2, and so forth. Xk equals y sub k. So in other words, another way of saying this is if you have a sequence of linearly independent vectors, a vector has a unique representation as a linear combination of v1 up to v sub k. So what is the proof of this? Suppose we have x1, v1, maybe just to make it very explicit, let me just do this in the case k equal 3. So suppose x1, v1 plus x2, v2 plus x3, v3 is y1, v1 plus y2, v2 plus y3, v3. So that's the same as saying the difference of these vectors, if I subtract them, is the zero vector. But I can rearrange this. This is x1 minus y1 v1 plus x2 minus y2 v2 plus x3 minus y3 v3. That's equal to the zero vector. But what is this? This is a linear combination of v1, v2, and v3. So we have this is a linear combination of v1, v2, v3 with coefficients x1 minus y1, x2 minus y2, x3 minus y3. But if the vectors v1, v2, and v3 are linearly independent, the only linear combination equal to 0 is the one where all the coefficients are 0. So x1 minus y1 has to equal 0, x2 minus y2 equals 0, x3 minus y3 equals 0. So this means x1 equals y1, x2 equals y2, and x3 equals y3. And that's the proof. That's done. Okay. So this is a very important property of linearly independent vectors. Let me show you one very nice connection between the big theorem on homogeneous linear equations and vector spaces. Suppose we have positive integers m and n, and n is bigger than m. So the theorem says that every sequence v1, v2, v3, vn of n vectors in the vector space Rm is linearly dependent. Not independent, but dependent. So if you have the vector space Rm and you have more than m vectors, those vectors must be linearly dependent. So for example, if I take n equal 3 and m equal 2, this says that every 3 vectors in R2 must be linearly dependent. And how do we prove this? Proof. So for each of these vectors, for j going from 1 up to n, we have the vector vj, and this is some vector in Rm. So let me write this as a1j, a2j, down to amj. That's a vector in Rm. They're m coordinates. So if we have the equation x1 v1 plus x2 v2 up to xn vn equal to the 0 vector, this is equivalent to x1 times A1J, A2J, sorry, A11, A21 down to AM1 plus X2 times A12, A22 down to AM2 plus X3 times A13, A23 down to AM3 up to finally Xn times A1N, A2N down to AMN equal to 0 vector. But this is equivalent to, see, if I add these vectors up, what do I get? I get A11x1 plus A12x2 plus A13x3 up to A1nxn. The second coordinate, I get A21x1 plus A22x2 plus A23x3 up to A2nxn, all the way down to the last equation, or the last coordinate, AM1x1, AM2x2, AM3x3 up to AMNxn. That's my vector equal to the 0 vector. That's the same as the system of two vectors are equal precisely when they have the same coordinates. So the first coordinate on the left is A11x1, A12x2 up to A1nxn equals 0. Second coordinate all the way down to the nth coordinate. And here, what we have is a system of m equations, m homogeneous linear equations in n variables, and n is bigger than m. And if you have a linear system with more variables n than equations m, there is a non-zero solution, x1, x2 up to x sub n, which means the vectors v1 up to v sub m are linearly dependent. That's the theorem I wanted to prove. So in the vector space Rm, if you take more than m vectors, they must be linearly dependent. Right? Whenever you have subspaces of a vector space, there are different ways to construct new subspaces from them. So suppose we have a vector space V with subspaces W1, W2, up to W sub k. The intersection of all these. What is this? What does the intersection of the sets mean? This is the set of all vectors W in the vector space such that W is in the subspace Wi for all I from 1 up to k. Right? That's the intersection. This is a subspace of V. So here's kind of a picture. Suppose this is the vector space V. Here we have W1. Here we have W2. This is the intersection. That's going to be a subspace. If we had a third subspace, even W3, then the intersection of W1, W2, and W3, the points that belong to all three sets are shaded in red here. So this red is that. That's the intersection of those three subspaces. That's kind of a picture of what we're talking about. And the sum set. So I'll write this as W1 plus W2 and so forth, plus W sub k. So this is the set of all vectors that can be written in the form little w1 plus w2 and so forth, plus w3, where each of these wi's is in the subspace w capital Wi for all I from 1 up to k. That's the sum set. Let's see. Harder to draw a picture of this. Suppose we're in three-dimensional space. So this is R3. And suppose W1 is the x-axis. So that's the set of all vectors of the form x, 0, 0. And suppose W2 is the y-axis. Then what is W1 plus W2? It's the set of all vectors of the form x, 0, 0 plus 0, y, 0. For all x and y, if you had this is just x, y, 0 for all x, y, and r. That's the xy plane. So in R3, you have the x-axis in this example, that's W1. The y-axis is the subspace W2, and the sum set W1 plus W2, it's the xy plane, all the vectors with z coordinate equal to 0. That's an example of a sum set. Right. Why is the intersection of subspaces a subspace? So let's give a proof. So I'm going to prove by induction on K that W1 intersect and so forth up to WK is a subspace. So let me start with the case K equal 2. So we have W1 and W2 subspaces. And we must show the intersection is a subspace. So first of all, every subspace contains 0, the vector 0. So 0 in W1 and 0 in W2 implies 0 is in the intersection, because the intersection is all vectors that belong to both W1 and W2. What about vector addition? If W1 and W2 are vectors in W1 intersect W2, that means that W1 is in W1 and W1 is in W2, because it's in the intersection. And if W2 is in the intersection, W2 is in W1 and W2 is in subspace W2. But W1 is a subspace, so W1 plus W2 is in the subspace W1. It's closed under vector addition. And similarly, if W1 and W2 are both in the subspace W2, W1 plus W2 is in W2. So W1 plus W2 is in both of these subspaces, so it's in the intersection. So the intersection is closed under vector addition. Similarly, if C is a scalar and W is a vector in W1 intersect W2, then W is in W1 and W is in W2, which means CW is in W1 and CW is in W2. And you put that all together and you get CW is in W1 intersect W2. So W1 intersect W2 is closed under scalar multiplication. So this intersection of two subspaces contains the 0 vector, is closed under vector addition, is closed under scalar multiplication, therefore it's a subspace. So suppose this is what's called induction. K is an integer greater than or equal to 2, and the intersection of K subspaces is a subspace. Suppose I have the intersection of K plus 1 subspaces. So this set is the same as the intersection of the first K subspaces with the K plus first. By the induction hypothesis, this is a subspace, and this is a subspace. So this resulting thing is a subspace. So once you prove the theorem for two subspaces, it's very easy, very quickly true for any finite number of subspaces. Okay. Any questions about any of that? Okay. There are a few more results I want to prove today, which is like this week. So this is theorem 110 that that V be a vector space. Yeah. That V be a vector space. And let S be a non-empty subset of V. The set W of all linear combinations of vectors in S is a subspace of V. So proof. Suppose S, so this is the basic case. S is a finite set, not an infinite set. So S consists of vectors, say W1, W2 up to WK. So if I take 0 times W1 plus 0 times W2 and so forth, plus 0 times WK, that's a linear combination, and that's the 0 vector. So that's in W, because W is all linear combinations. And if you have, say, scalars, if say you have C1W1 plus C2W2 plus C sub K WK is some vector in W, and C1 prime W1, C2 W prime plus C sub K, C1, C2 prime, C sub K prime WK is also in W. Suppose I call this vector W and this vector W prime. Then the sum W plus W prime, if I add them, I get C1 plus C1 prime, W1, up to CK plus CK prime, WK, is in W, because the sum of two linear combinations of the vectors W1 up to WK is another linear combination of the same vectors. So the set W is closed under scalar multiplication. And if I take the vector W and I multiply it by a scalar A, this is A times C1W1 plus CKWK. So that's just AC1W1 up to ACKWK. This is again a linear combination of my vectors W1 up to WK. So that's in W. So W contains the 0 vector. It's closed under vector addition, closed under scalar multiplication. So W is a subspace. And if S were infinite, when you take two vectors that are linear combinations, every linear combination is a linear combination of a finite set of vectors. So this reduces to the case of a finite set of vectors again, if you think about it hard for a while. And that's the proof of the theorem. And we call W, we call this space the subspace of V generated by S. It's the set of all linear combinations of vectors in S. And in fact, it's a very nice result. And we denote this by S in brackets. So what we have is so S is a subset of a vector space V. Brackets S is the set of all finite linear combinations of sets of vectors in S. And this is a subspace. So this is the subspace of V generated by S. And there is a very nice characterization of this. This is a theorem. So we have S contained in V. Suppose we let script W be the set of all subspaces W contained in V such that S is contained in W. So you look at all subspaces of the vector space that contain S. So there's then the theorem says that the intersection, so if you call this, say, W sub I in the set I, so we just index them by some set. This is the set of all subspaces that contain V. The intersection of all of these W's is S. So the subspace generated by a set S of vectors is the intersection of all subspaces of the vector space that contain the vectors. And so the proof goes in two directions. First, S is contained in W, because W is a subspace that contains S. Subspace contains all linear combinations of its vectors. So the subspace generated by S is contained in W. So the subspace generated by S has to be contained in the intersection of all such subspaces W. On the other hand, also S is contained in the subspace generated by S. So the subspace generated by S is in the set W, script W. So the intersection of all the subspaces in W is certainly contained in S. So we have contained in subspace generated by S. So this inclusion and this inclusion imply the intersection of all the subspaces that contain S is the subspace generated by S. That's the theorem. All right, well, we've done a lot today, but again, we're doing a week's work every day. And there's a great deal to think about in this lecture. So you really need to spend a lot of time trying to understand this material. You have the notes that I've posted on Blackboard, and you also have another textbook on Blackboard, which is a kind of a secondary source, and you're encouraged to look at that and any other book you might want to look at, because the more you read and the more you think about the subject, the better you'll understand it. Okay. Any questions before we quit for the morning? If not, we're done. I have a problem session office hour for whoever's interested, scheduled at 7 o'clock tonight and also tomorrow night. But I'm also, of course, as you know, available at the beginning of every lecture, 9 o'clock, to answer questions also. Okay. See you perhaps tomorrow. Bye all.